Today's topic is just crystal structure. This is the third class of crystal structure, a part of solid-state physics. Now, we have learned about unit cell, crystal planes, Miller indices. Now, so if you learn about the crystal planes, now we are going to discuss a special type of crystal, that is cubic crystal. Now, what is a simple cubic crystal? Plainly called simple cubic. We have just a cube here, and all the corners of this cube can have single atom. Okay, so each corner of this cube contains single atom. Now, if you consider this A atom, now this A atom is a part of this unit cell, and if you see here there is another unit cell. Okay, there is another unit cell, and of course here in this part, so this is unit cell number 2, this is 1, this is 3, and this is 4. So this atom is basically a part of this 4 unit cell, and not only that, this atom is a part of other unit cell also, which is lying on this surface. Okay, so if you consider this atom, what is the contribution of this atom? So there is only one atom, and each atom is a part of 8 unit cell. So if this is a part of 8 unit cell, so total contribution of this atom for single unit cell is 1 by 8 times. Okay, now each of this, if you consider all the atoms at the corner, so each of the atom contribute just 1/8 portion of this cube. Okay, so as all the atoms contribute 1/8, so total number of atoms is 8. So simple cubic has only single atom per unit cell. So 1 atom per unit cell is the simple cubic. Now, if you consider a face-centered cubic, axis crystal. So face-centered cubic, there is a cubic structure, right? Now, corner, there exist 8 atoms in the 8 corners, and each of these face have single atoms. So there are 6 atoms on the 6 face, right? So 8 corner atoms, these are corner atoms, and 6 face centered atom, right? So in case of simple cubic, as the contribution of each atom is 1/8, so in this case also the corner atom contribute 1/8 portion of to this unit cell. So 1/8 times 8 atoms. So each of this corner atom, so total contribution of this total corner atom for this particular unit cell is 1/8 into 8. Now each spatial atom is a part of 2 unit cell. So this atom, if you consider this spatial atom is a part of this unit cell and its neighboring unit cell. So if you extend this unit cell in this way, what you will get? You will get that this atom is a part of this unit cell and this unit cell. So contribution of this atom is just half for each unit cell, and there exist total 6 atoms. So 1 plus 3, there is 4 atoms per unit cell. So this is face-centered cube. Now if you consider a body-centered cube, what happens? For a body-centered cube, each corner of this cube have single atom, and there is an atom at the center of this unit cell. Okay, so contribution of each corner atom is 1/8 into 8 plus, as this atom is situated at the center of this cube, so the contribution of this atom is just 1, right, as this atom situated at the center of this unit cell. So total contribution of this total atoms for this unit cell is 1 plus 1, that is 2. Okay, so simple cubic contains single atom per unit cell. Face-centered cubic contains 4 atoms per unit cell, and body-centered cubic contains 2 atoms per cell. Right? Now, if you can calculate all types of atoms, that is number of atoms for per unit cell, if you calculate for every type of crystal system. Now, what is a crystal plane? I have said earlier, crystal plane is a particular plane in the Brevis lattice that contain at least 3 non-collinear atoms. So, in the Brevis lattice, crystal plane is a plane. It contains at least 3 non-collinear atoms on it. Okay. Now, as we consider that, we imagine that there exists some plane in the crystal for our mathematical proposition. If you consider that there exists some plane, so those plane must have some interplanar spacing. Okay. Now, what is the interplanar spacing? Interplanar spacing is just the perpendicular distance between two adjacent planes. So, it is the perpendicular distance between two adjacent planes is called. So, let us assume that these are two planes. Now, this distance is called the interplanar spacing. Okay, so if you consider this family of planes is 1, 0, 0, now this T100 is the interplanar spacing between the family of planes 1, 0, 0, right? Okay, so now you have to calculate the interplanar spacing of given cell. Okay, so let us choose first a cubic crystal. And for this cubic crystal, so calculation of interplanar spacing. Now consider this is the coordinate system or coordinate system which coincide with the three adjacent axes of unit cell. Now those unit cell, there must be at least three non-coplanar vector by which those unit cell can be framed, right? So these three axes are just coincide with the sides of that unit cell. Now you consider a plane here. Okay, so this is the plane. Now you can draw the normal on the plane which is passing through the origin. So let us consider that this is the normal on the plane. This is passing through the origin. Now if this is normal of the plane, now this ABC, if you consider this as a ABC plane, and this ON as the normal, then I can say that this angle as alpha, this angle as gamma, and this angle which is made with this normal is beta, right? So alpha is the angle between this x-axis, we assume that this x-axis, this y is z. So alpha is the angle of this normal with x-axis. Beta is the angle between this normal and y, and gamma is the angle between ON and OZ. Now we have to apply the condition of direction cosine here. And before we going for the direction cosine, so what is the length of this distance, that is OC, if this plane intersect on this three axis of a unit cell? Now if this happens, then I can say that three intersection of this plane is basically, as this is HK will be the mirror indices of this plane, so I can make the reciprocal, then make this H scale to its closest integer to get this H scale. So as we frame this H scale by some rules, so the intersection of this portion, that is OC, must be C divided by L if ABC are the unit cell parameter. Okay, so if ABC is the unit cell parameter and H scale is the Miller indices of this plane, the intersection OC must be C divided by L. The intersection OA, this is along X direction, so that should be A divided by H. And intersection OB, this is obviously B divided by K. Okay? So if this happens, then I can say that if this is the angle alpha, then what is the value of cos alpha? cos beta and cos gamma. Now cos alpha is this is normal to the plane. So if you draw this line, so as this is normal, this angle is 90 degree and this is the hypotenuse. So this will be ON divided by OA. So ON divided by OA. What is the value of this cos beta? This cos beta will be this ON divided by OB. So ON divided by OB. Now the value of cos gamma will be ON divided by OC. Right? So if these are chosen in this way, and I can write that if any plane that are having mirror indices H, K, L, so another plane that can go through the center, that is through this origin. Okay, so the distance between two planes is just ON. This is this normal. So if this is the distance between two planes, then I can write that this ON must be equal to B. Am I clear this portion? That ON is the perpendicular distance which passes through the origin. So if you choose any plane which is ABC, another plane must pass through this origin. Okay, so this is Intervenor Spacing. Now this ON will be D divided by OA. OA means here I can assume that OA, which is A by H. So H D by H. So in case of cos beta, I can say this is ON by OB. So B divided by B by K. So this is K D by B, and ON by OC for cos gamma, and this will be D divided by C by L. So this will be DL by C. Right? Now, as these three are the direction cosines of that particular axis or particular plane, so I can say that cos square alpha plus cos square beta plus cos square gamma, this must be equal to 1. So if you put that particular thing, so h square by d square by a square equal to a square by into d square by b square plus l square d square by c square equal to 1. Right? Now if you bring that d, so this will be h square by d square plus a square by d square, h square by c square, this will be 1. Okay, so d will be 1 divided by just, so this is d square, sorry. So h square, a square, a square, b square, h square, c square to the power half. Now for a cubic crystal, if you choose a special case, now for a cubic crystal, this A, B, C equal to A. So A equal to B, to C equal to A. So for simple cubic crystal, just interpreter spacing becomes A square or A divided by root over A square plus A square plus H square. So this is the interplanar spacing of a crystal. Now if you calculate this interplanar spacing, immediately you can calculate for the interplanar spacing for a cubic system. Okay, or cubic crystal, I can write. Now, what is the interplanar spacing of D100? This is family of planes of 100, D110, and D111. Okay, so these three planes does not have the same interplanar spacing. So what is the formula? Formula is DHKL, obviously this is Miller indices. So DHKL equal to A divided by root over H square plus A square plus L square, right? So as this is H square plus A square plus L square, now you can put for D100. So D100 will be A divided by root over 1 plus 0 plus 0. So this will be just A. Okay. Now for D110. So D110 will be A divided by root over 1 plus 1 plus 0. So A divided by root 2. So A divided by root 2 is just the interplanar spacing of D100. Now for D111, this spacing will be A divided by root over 1 plus 1 plus 1. So this will be A root 3. So the ratio of that interplanar spacing of this 3, that is D100, D110, D111 will be 1:1 by root 2. Okay, so for cubic crystal, these are the just interplanar spacing of three different family of planes, that is 100, 110, and 111. Okay, now what is the density of a crystal system? Okay, so calculation of density of lattice point in lattice plane. Okay, so this is just a calculation of density of lattice point in the lattice plane. So consider that there are capital N number of planes that exist for a specific type of Bravais lattice, and A is the area of cross section of each plane. So each plane have A amount of area, and D is just interplanar spacing. So if this exists, now the volume of lattice space. What are the volume of this lattice space? So there are n number of planes, each of area A, and D are the interplanar spacing. So if you multiply this area with D, you will get the region, the volume between two planes. So volume between two planes that is adjacent obviously, this will be area times D. So total volume of that, if there exists total n number of plane, so this is NAB. So NAB represent the volume of that lattice space. Now, if capital V is the volume of each unit cell, if capital V is the volume of each unit cell, then number of unit cell, so then I can say that the number of unit cell is equal to NAD divided by V. So this is total number of unit cell in the lattice space, right? Now, say for example, each unit cell, if each unit cell have small n number of lattice points, okay, if each unit cell have small n number of lattice points, then I can say that total number of lattice point in the lattice space, so total number of lattice points in the lattice space, what is its value? Just n times this total number of units. So A, capital N, AB divided by V. So these are the total number of lattice points in the lattice space. Now if there exists total n number of lattice points, and if you consider that rho is the density of lattice point, so each lattice points have got a density rho, then you can say that total number of plane is capital N, A is the area, and density means per unit volume there exists n number, a rho amount of lattice point. So I can easily say that the total number of lattice point in same lattice space will be n A times rho. If rho is the density, then n A rho is the total number of lattice point, and this total number of lattice point in A rho must be equal to this total number of lattice point. So this is equal to n capital N A B on V. Okay, so what is the value of that density? So just remove this. So rho equal to small n D divided by V, where small n is the number of lattice points in each unit cell, D is the interplanar spacing, and this V is the volume of the crystal, right? So for cubic system, as for cubic system, we have to calculate just use simple cubic. So for simple cubic system, this volume is a cube. Okay. Now if this volume is a cube and total number of lattice point per unit cell is 1. Okay. So rho will be just T by A cube. Okay. Now for orthorhombic system, there A not equal to B, not equal to C, but alpha equal to beta equal to gamma equal to pi by 2. Right? Gamma equal to pi by 2. So you can say that for orthorhombic system, this rho will be D divided by A, B, C. And if this is just primitive cell, or primitive cell, if this is non-primitive, then it depends on the number of lattice point present per unit cell. Okay, so these are the density of lattice point for a specific crystal system. Now, I am just discussing about atomic packing fraction. Okay, so what is the packing fraction? Packing factor, right? Packing factor. So what is the packing factor? Packing factor is the ratio of volume of atom per unit cell, that is the volume per atom in the unit cell, small b, divided by total volume of unit cell. This is just a packing factor. Now, as each type of crystal system contains different type of a different number of lattice point per unit cell, as I called, the density becomes different. So this packing factor must be different for different type of system. If you choose hexagonal close pack, we are not going in detail about hexagonal close pack, but for hexagonal close pack, it is not a loosely bound, but it is tightly bound structure, because in that case packing fraction value is much higher, and in case of face-centered cubic, this packing factor had higher value, that is approximately of the order of 0.74. I will come to this later. Now, for a tightly bound structure, this packing factor represents the how much the structure is basically stuffed within the unit cell. Okay, so let us calculate this packing factor for some for cubic crystal system. So assume first cubic system. So first, that is tight bound structure. So this is face-centered cubic. Now for face-centered cubic, what it will do that if you choose one face of that cubic system, the face looks like this, right? Now I will choose this corner and a circle. Okay, there are atom obviously present at this corner and this corner, but this is a portion of the total atom that will contribute for this index. Now the radius, if you choose radius is r, the radius of this atom is twice r and radius of this atom is r. So 4 times r, this distance will be equal to just the diagonal of this cube. Okay, so if this cube have length a, then this 4 times a will be equal to the diagonal. So root over a square plus a square. So root 2a, right? So if it is root 2a, then the value of r will be root 2 by 4a. So a divided by 2a. So radius will be a divided by 2 root 2. Now what is the value of packing factor? Now packing factor, as there is this r equal to a to root 2, then I can say that the volume of each atom I assume that atom is obviously circular, so spherical, 4/3 pi a divided by 2 root 2 is q. Okay, and now volume of 4 atoms, as there exists total 4 number of atoms per unit cell. So this will be 4 into 4/3 pi a divided by 2 root 2 q, and this will be pi root 2 a cube by 6. So if you calculate, just simplify this, pi, so pi comes out root 2 a cube divided by 6. So for FCC, the volume, or will get the volume of atoms per cell, that will be pi root 2 by 6 into a cube. Now the total volume of this unit cell is a cube. So packing factor in this case, that is pi into a cube by 6 by a cube. So this will be just pi into by 6. Now if you calculate the value of these things, this will be approximately 0.74 approximately. Okay, so these are tight bound structure. Now if you consider a B.Sc, that is body centered cubic structure. Okay, so second example is for a body centered cubic structure. Now if you consider this body centered cubic, then this is the unit cell and the atom lying at the center and atoms are lying at this, we are at the center and at this corner. Okay, so this is the body diagonal of the cube. So AB, if you consider this AB is the body diagonal of this cube, and as this is body diagonal of this cube, so I can say that R plus twice R plus R, this will be A, this will be root 2A times this A, this will be root 3A. Now R will be root 3 by 4. Okay, so for body centered, this will be root 3 by 4A. Now each cell, so atoms per unit cell for body centered cube is 2. So volume occupied by atoms in this B.Sc cell, this will be 2 times, as there is 2 atoms, 4 third by root 3 by 4A cube, right? As this is the radius of each atom. Now volume of that particular cube is a cube. So packing factor will be 2 into 4 third pi into root 3 by 4 its cube. Okay, so this will be pi root 3 divided by 8. Right? So, and the value of this pi root 3 by 8 is almost 0.68. So, the packing factor of body centered cubic is 0.68. Now, if you assume the packing factor of simple cubic, so this is basically simple cubic, and each corner have this kind. Each corner contains this type. So it is not. Now this is R, this is R. So 2R equal to A for simple cubic. So R equal to A divided by 2. Okay, so as R equal to A divided by 2, so the volume will be of atoms in the simple cubic 4 third pi A by 2. So okay. Now packing factor will be 4 third pi 1 half. Okay, so this will be pi by 6, and the value of this is approximately 0.5. So for simple cubic, this is the value of packing factor, that is 0.52. Okay,